Hello everyone, we are Group 14. This is our report, Comparative Electrocatalytic NRR Performance of MoS Quantum Dots vs Doped MoS Synergistic Effect and the Communistical Insights. This is our outline. Number one is introduction. Number two is MoS as quantum dots. Number three is Doped MoS. Number four is conclusions. Number five is reference. NRR is an electronical process that reduces nitrogen to ammonia under ambient conditions. It offers a greener and more energy efficient alternative to the traditional Haber-Bosch process, which is high energy intensive and contributes to CO2 emissions. NOS2 is two-dimensional layered material known for its excellent popular candidate for the electrocatalytics due to the tunable electronic structure abundance and the chemical stability. In this project, we amount to explore how different modification of NOS2, namely quantum dot formation and the doping, affect its catalytic performance in NRR. Ammonia is essential chemical for global agriculture and industry, widely used in fertilizer, force, and various chemicals. The current industrial process Haber-Bosch is high energy intensive and emits a large amount of CO2. Therefore, developing a green ammonia synthesis pathway, such as nitrogen reduction reaction, is a major focus of current research. As shown in the first slide, this involves catalyst design, renewable energy integration, and magnetic understanding to create a sustainable M2T and A3 conversion system. In this context, molybdenum disulfide NOS2 has engaged as a promising catalyst. The second slide shows its layered crystal structure, where M represents a transition metal like Mu or W, and the X represents chalcogen atoms such as S or Se. This structure enables tunable catalytic properties, making NOS2 and its quantum dot from attractive candidates for electrical.
In this part, I will highlight a key study by Law published in Chemical Communication in 2021, which systematically investigates electrocatalytic performance of MoS2 quantum dots for nitrogen reduction. The motivation behind the work is clear. Conversion of MoS2 nanosheets show limited NRR activity due to their low number of export achieved site and poor nitrogen absorption capacity. To overcome this, the author designed ultra-small MoS2 quantum dot to take advantage of quantum confinement equation and the high density of edge site. This quantum dot was synthesized via a hydromercyl metal, result in the uniform structure with an average diameter of around 2.5 nanometer. Compared to block MoS2 or even nanosheet, the quantum dot had a much higher sulfur to volume ratio with significant enhanced catalyst performance. In their electrochemical test, MoS2 quantum dots achieve an ammonia yield rate of 39.6 mg per hour per milligram and a flat efficiency of 12.9% at minus 0.3 VVS-IHE. These values are not only spread of or to loss of MoS2 nanosheet, but also compared with many other report NRR catalysts. To understand the mechanism, the team conduct DFT calculation have shown that the quantum dot strong N2 absorption through a site on the configuration at the HMO site.
I'd like to introduce which is the field of electrotechnical nitrogen reduction, and this paper is published in ACS Applied Nanomaterials in 2022. And this research presents novel nanomaterial, and its name is called sulfur vacancy, and iron doping MoS2 of the substrate of carbon, which stands for iron doping sulfur vacancy rich, and with 1T2H mix space, and MoS2 carbon nanofar. This space is to carbon nanofar notification behind developing this material is to overcome the limitation of a traditional Electrocatalytic in allow such as to conductivity, insufficient active site, and low selectivity. The 1T2H misfits junction combine the high conductivity of the metal hetero magic place with the catalytic activity of the hetero 2H place. The hardware flexing has both electron transfer and the number of flexi variations is high. Over vacancy introduced by the BH4 treatment acts as zero charge defense by this vacancy facilitates molecule absorption and activation by weakening the nitrogen bond, which is critical for the NRR. And we can see below the SV curve indicate the sulfur vacancy around 1T2H has MoS2 and Carl Scott status tree. It's her excellent catalyst performance. This lower onset potential suggests that the hot grade promise of practical application. And iron doping modifies the electronic structure of MoS2. The formation of iron, MO, and sulfur bonds turn the energy landscape of the catalyst, improve nitrogen binding, enhance the selectivity of the amine formation, and suppress combating hydrogen evolution. The performance was the sulfur vacancy iron MoS2 catalyst achieve an impressive near yield rate of 17%. It finds 0.5 volt. This is actually with a periodic efficiency of 9.2% at minus 0.3 volts under ambient conditions. This result outperforms both untolerant and the non-effective transit power, clearly demonstrating the injustice effects of the fast missing concealed energy and the met doping.
This part is conclusion. Conclusion of MoS2 quantum dots. The first one, the high density of explore H site in the quantum dots. A second, enhanced interreaction between MO and the nitrogen due to reduction domination. The third, and the ability of a quantum dot to stably intermediate space during the reduction step.
And our material design features three key elements. First, iron doping regulate the electronic structure, improving nitrogen absorption and ammonia selectivity. they can sulfur vacancy, create active defect sites, and facilitate nitrogen bond cleavage, and promote reduction. Finally, the 1T2H phase combine high conductivity with strong catalytic activity, enhancing electron transport and the overall reaction efficiency. And it is our reference. And this is all of our presentation. Thank you all.